Wait a minute, and wait a minute. Jonathan, are you talking too?
I'm talking.
Okay, all right.
So I'm not David.
When we're here, you need to advance using this.
So I'm Jonathan Obiston from the Army Corps of Engineers, and I'm going to kick off David's talk, primarily because it was almost a decade ago that the Army Corps of Engineers, the Albuquerque district, kicked off this idea of let's look at a sediment model of the Middle Rio Grande to see if we can tease out some ways that how geomorphology changes with time, because we've seen changes on the river. And so to do that, we ended up with coming up with a model, and the sediment model makes some sense, and then there's limitations with it, but it transports sediment, and we get a sense of how much sediment is moving and where it's moving and how we can assess things. And so this is just a view of 3 different aerials from 1999 through 2018, just above the I-40 bridge. And you can see in 1999, there's still a lot of sandbars that are mobile, and that's all your sediment load coming in, and it's getting settled out there. And then you see over time that those don't get moved as much, they get vegetated, they get anchored to the bars, and your river gets narrow. And so that's kind of the stuff that we wanted to see. How is this changing over time? And we ended up with this 1D model that David will talk about more. But I wanted to touch on why sediment? Why talk about a model with endangered species? What does it even matter at all? And I would argue that sediment is equally as important as water in developing habitat along the Middle Rio Grande. This picture on the left here, where you see the dense vegetation, all that vegetation that has in our bosque deposited on sediment that deposited sometime in the 30s and 40s and 50s. So the sediment, when it becomes still, becomes a vital portion for our vegetation. But you also have so this is one of our bosque restoration sites, and you can see where the water is inundating. It's very turbid, so that it brings in a layer of fines in these overbank areas that when the water recedes, it kind of seals things in and retains moisture and allows the vegetation to grow faster. And then you have tributaries like the Calabasas that bring in a lot of sediment, and that gets distributed over time in the river and changes and makes it a more dynamic environment. And that's the kind of stuff that we wanted to tease out when we began this effort. And it's been a lengthy process, but we finally wrapped it up, and David, I'll turn it over to you to talk more.
Thanks, Jonathan. So for just general extent, it's about 170 river miles, starting at the upstream end, just below Cochiti Dam, and going down to the headwaters for Elephant Butte Reservoir, about river mile 60. So it was a continuous model, but because that's an unwieldy workspace, we broke it up by reaches, kind of at the 3 diversion dams. So this is just to give you a sense of the length of the 4 reaches and the contributing tributaries that were modeled within each reach. Well, the one technical part of this, with sediment, start at the bottom there, the total sediment load. What we were interested in, if you head to the right there, the bed material load, the sands and coarser. We did not evaluate silts and clays as part of this model. And as Jonathan said, it's been about a decade. The Corps' been contributing to the collaborative program, at least the work we've been helping them with, started in 2012 with this preliminary data collection and assembly. And what that figure on the right is showing is the y-axis is the number of sediment samples available, the x-axis is river mile, and the colors, the green colors are more recent after 2005. So as part of this initial collection, we realized that we didn't have a good consistent set of sediment data that was available. So we set out to collect that, and we also did a bunch of surveys of jetty jacks and how much sediment was stored in the floodplains. That was followed here in 2013 by a tributary sediment yield study. So this plot here in the lower left is just a sediment yield relationship with drainage area on the x-axis and mean annual bed material yield on the y-axis. So this became a really important input to the mobile bed, the sediment model. So we had to start with these precursors, developing the needed information. As we get into the basic model setup, what we've got in the top left is the Bureau of Reclamation's aggregation degradation data sets, which are cross-section, it's geometry. So we needed to represent the channel morphology, and that was a important source of the geometry. In the lower left is a plot that represents the hydraulic calibration of the models. So before we got into running sediment, we wanted to make sure that we had the hydraulics squared away. And what we're looking at on the right there, the photo represents, as I was telling you, we realized we needed to do a bunch of bed material sampling for the model. And that is just an example of one of the sites where we collected both surface and subsurface samples. So there was hundreds of samples that were collected as part of this project. And the figure kind of inset behind it is a sediment rating curve at the Bernardo gauge. So the green points on that curve represent the USGS's measurements of sediment transport passing Bernardo. The blue points there represent our model, one of the scenarios we ran. So showing that in addition to hydraulic calibration, we were very focused on geometric change as represented by the AgDeg cross sections, as well as sediment loads and gradations passing the USGS gauges. As Jonathan mentioned, it's a 1D model. There are limitations, we recognize that. The top right there is the sediment plug that formed just recently down at the Elephant Butte Narrows. We don't have the ability to simulate sediment plugs. That's not a 1D phenomenon. And with the channel narrowing, the response that we get in our model is manifested either as degradation or aggradation of the bed. But in terms of a volumetric change, we believe that we have represented volumetric change, and whether that's a narrowing or a aggradation, we don't have the ability with a 1D tool to show that direction. So we looked at a bunch of scenarios here. The table in the top right, you can see the headers are the 4 reaches, and then pointing out that we did a calibration run and a validation run. We compared our results to observations to make sure we were comfortable with what we were seeing. And really the statement there that the value of this approach is comparative. So we did a baseline scenario, which represented 37 years of hydrology and sediment. And we ran that 37 years in the future and said, that's our baseline scenario. Then we had predictive scenarios where for that same period, we made some type of change. For example, we looked at a reduced snowpack scenario. We also looked at, as you get farther downstream and toward the San Acacio Reach, the River Mile 83, a restoration project. We looked at the influence of Elephant Butte's pool elevations. So as you work downstream, there was just more factors that could influence results that we evaluated. So the chart here on the left just shows for the reduced snowpack, this is the comparison to the baseline. The blue bars represent on an annual basis, the reduction in runoff volume, and the green line is the cumulative. So for that scenario, it's approximately over the 37 years, it's a 7 million acre-foot reduction in runoff pushed through the model. So it's really important that we're using this to compare back to a baseline scenario. I want to show this is some of the results from the validation. So what we have on the x-axis is the mean bed elevation change. And the green line represents our prototype. This is the information available to us as the observed change between 2002 and 2012. The blue line is the model simulation, the results. And what I want to point out is it was really important for us, what we feel like is the contribution to models that are already available is that this model, we wanted to make sure was set up with consistent parameters from top to bottom, and that we didn't reset our boundary conditions at the diversion dams. So we had the results from the Cochiti Reach became the input to the Albuquerque Reach. The results from the Albuquerque Reach become the input to the Isleta Reach. So it doesn't allow you to hide your sins by resetting your boundary conditions each time. And what that means is it's more challenging, and we accepted more divergence from the prototype in individual locations so that overall we had something that we thought was consistent. This is a similar plot, but instead of bed elevation change, the y-axis is the cumulative channel mass change. And again, the green line is the observation and the blue is our simulation. So this goes to show you that you might not want to take this model and try and say, there's exactly 4.3 feet of change right there. That's not the intent of what we've done. What it's showing is that overall, over these 4 reaches, we are generally representing these observations. So what the model has in it with the baseline and then these selected scenarios is that it really points out what is influential and what kind of responses we're seeing in terms of general aggradation and degradation. So I'm not going to read this to you. I'll leave that out there as just something that's interesting, and where I want to head with it is we've already taken this model. This is an example from the Isleta diversion dam. So down the lower end of the figure here, we have a bunch of information that the USGS has collected at the Central Avenue gauge. And we're working on a project for the Pueblo right now to evaluate sedimentation problems at the diversion dam and passage of Rio Grande Silvery Minnow. We needed that information from the USGS gauge down at the diversion dam. So this model became a tool where we input what was available up here and use the model to translate that information to us down there. And the plot here just shows that the sediment that was routed is overwhelmingly fine sand, medium sand, and coarse sand. That's what's being delivered to the diversion dam. And then another application is the Tiffany Fire Rehabilitation Planning Project. So the top left is the fire itself, and over on the right, the objective is going to be vegetative restoration, rehabilitation maybe to use Todd's word. And it's really going to be important for the viability of that vegetation and ultimately for it to produce flycatcher habitat, to make sure that we understand the nexus between bed change, water levels in the river, groundwater levels, and which types of vegetation will be successful. So this is another situation where we will be using this model to help inform that study. And so what I'm here today is just to help get the word out that this tool was out there and it's available. And if anybody is interested in has an idea of how it might help some pursuit that you're working on, Jonathan's your man. So his contact information is there. And with that,